A mortar fires a shell of mass m at speed v0. The shell explodes at the top of the trajectory, as shown by a star, as designed. However, rather than creating a shower of color flares, it breaks into just two pieces, a smaller piece of mass m 1/5 m, and a larger piece of mass 4/5 m. Both pieces land at exactly the same time. The smaller piece lands perilously close to the mortar at a distance of 0. The larger lands a distance d from the mortar. If there had been no explosion, the shell would have landed a distance r from the mortar. Assume the air resistance and the mass of the shell's explosive charges are negligible, and then find d in terms of r. So this is basically a center of mass problem. Because we neglect the explosive charges themselves, that's an internal force, meaning it does not change the motion of the center of mass. So the center of mass lands exactly where it would have landed before, which they tell us is a distance r. I'm going to say that mass m1 is the 1/5 mass object, and that has a distance of x1 equals 0. And then I'm going to say that mass m2 is 4/5 m, and it lands at a distance which is d, according to that, according to their drawings. So over here. And then the system itself has a total mass, which is just m, and lands at a center of mass position, which is r. And what we know is that we can compute the center of mass position based on the other ones, in that the total mass times the center of mass is equal to each individual mass times its position, all summed up. So here we have total mass m times position r equals 1/5 m. I don't know why I keep doing that. Something in my head has a quarter. 1/5 m times 0 plus 4/5 m times d, or mr equals 4/5 md, which means d must be 5/4 r, a little bit further than where the other guy lands.